Okay, the next couple slides are going to deal with equilibrium solutions for weak bases. This is exactly the same as weak acids. So earlier we took a look at acetic acid, for instance, and acetic acid was able to give off a proton in presence of water as your solution. And that basically generated hydronium ion and the corresponding conjugate base acetate, and that conjugate base is coming from the acetic acid unit. In this case, again, we are going to show the reaction of ammonia now with water, but turns out that ammonia is more basic, and so water ends up becoming basically acting as an acid. And you can say that it's a Bronsted-Lowry acid in this case because if you notice, you have the HOH bond, and what becomes of it is OH negative. And so when you compare the two species, you can say that it is one proton short, which is why we are saying that water is going to behave as an acid and ammonia is going to behave as a base. Now, if you just had to predict which one between ammonia and water, which one is a better acid, you would simply say that since across in a period the electronegativity that increases. So what that means is that the OH bond in case of water is going to be more polar as compared to the NH3 ammonia molecule. So the NH bond is going to be lesser in terms of polarity, and so it'll be easier for the OH to give off that proton, and the resultant conjugate base that you get, which is OH negative, that negative charge sits on the oxygen atom. You can say that that is much better placed by that oxygen, which is an electronegative element. So realize negative charges are better held by electronegative elements. Positive charges are better held by electropositive elements, or elements which are a little bit more towards the center. So things like carbon, for instance. Oxygen with a positive charge, never a good idea. Or fluorine with a positive charge, not a good idea. That fluorine or oxygen would want to get rid of that proton as soon as possible. So anyway, so now that we have figured what's the acid, what's the base, basically the species that loses the proton is the acid, and what you generate from there is a conjugate base. Likewise, the base picks up that proton and generates a corresponding conjugate acid. And I had said earlier that conjugate acids are positively charged, or acids could be electron deficient in nature if neutral. Likewise, when you're thinking about bases, you either are looking for a negative charge or source of electrons. Those electrons should be donatable. So in this case, that happens to be the lone pair of electrons on nitrogen. So if one tries to locate the just kind of write down the equilibrium constant for this equilibrium condition, one can say, let's just erase parts of it so we can make some room for ourselves. If you were to write down the equilibrium constant K, you will pick all the AQs, so that will be ammonium. Anytime you have a charge, by the way, consider that in aqueous. That will not be a liquid. Ammonia is going to be the denominator. Of course, as previously discussed, we are not going to count water, and the reason for that is, you got it right, the concentration of pure liquids and pure solids does not change, so we do not include that in a equilibrium. And so this particular K has a specific name. It's the base dissociation constant, so we just put a subscript K, subscript B, or KB. So just as previously we discussed the Ka for the acid, Kb is for the base. Stronger bases will have higher Kb values. That means they will have a potential to be more in the forward direction. That means they generate boatload of hydroxide. And that automatically means that the pKb is going to be lower as well. Now, one thing that I would like to say here is that while the steps are exactly the same that we discussed in the ice problems, to determine the pH values of solutions, provided you're given the initial concentration of acid and Ka value, you can calculate, you can use actually initial concentration and the pH of the solution to even determine Kb values, or vice versa. You can use Kb values and determine the pH of the solution. The only thing you should kind of think about is that in this particular situation, we don't really have an H plus going on directly. We have an OH negative, but you also should remember that pH and pOH are connected. So if you're able to determine pOH of the solution, since pH plus pOH is equal to 14, there's an additional step that you need to know that you can use to determine the value of pH. And once you have your pH, you can always just take the 10 to the power of negative pH. So take the anti-log, and that should give you the value for the hydrogen ion concentration. So just one added step there, but you should be able to get your solution pretty quickly. Okay, let's take a look at an ice problem. Um, the question is, calculate the pH and the concentration of all species present in 0.40 molar ammonia. The Kb value is provided as 1.8 times 10 to the power of negative 5. Write that down. So our initial concentration given is 0.4 molar ammonia. Your Kb value is given as 1.8 times 10 to the power of negative 5. And you're trying to figure out its ammonia that you have been given. It's an aqueous solution. That means it's basically the reaction that we just wrote. So if I were you, I mean, anytime you're given an ice problem, take the time to write down the reaction. And so maybe you should start calling it a rice problem. And that's a reminder that you have to write down the reaction first and then determine the I, C, and E, the initial change and equilibrium for that reaction mix. So ammonia, recall, is aqueous, that's a solution. Water is liquid. Anything that's charged automatically will be aqueous. So we are set with our equation. So that's the first thing that you should think about. The concentration initially is 0.4. Of course, it's a weak base, so you're not going to see any ammonium or hydroxide. And then you're assuming that if X moles are going to go through the dissociation, then X moles of ammonium and X moles of hydroxide will be generated, such that at equilibrium, what remains is 0.4 minus X. What gets generated of the ammonium is X, and what gets generated of the hydroxide is X as well. So now if you want to set up your Kb, you would say that it is ammonium times a hydroxide divided by ammonia. So plugging in values from the ice table, you would say it's X times X divided by 0.4 minus X. And of course, the value of Kb is 1.8 times 10 to the power of negative 5. Now, the question here is whether you can use the approximation or whether you'll have to solve the quadratic. So first things first, and every book will kind of give you, and even OWL will give you a different way, but all of them ultimately boil down to the same thing. So for me, what's easiest to follow is that I would look at the concentration, which is 0.4, and I would divide that by the K value, which in this case is 1.8 times 10 to the negative fifth. And if that number is more than equal to, if it's close to 100, then you will have to solve the quadratic. But if it is much more than 100, and in this case it would be, and you can run the math yourself, right now 10 to the power of negative 5 when becomes a numerator, that would become 4 times 10 to the power of 4 divided by 1.8. So that's like close to about 20,000, approximately 20,000. So that's a pretty big number. And so you can say that approximation holds true. Approximation holds, which means that 0.4 minus x is approximately equal to 0.4. And so you can neglect the x in the equation, and you can set up the rest of it as 1.8 times 10 to the negative 5 is equal to x squared divided by 0.4. And now when you solve this, you would say 0.72 times 10 to the negative 5 is equal to x squared, or 7.2 times 10 to the negative 6 square root of that is going to be x. So if you run the numbers on your calculator, and I have 2.68 times 10 to the negative 3 molar as the value of x. So x was a concentration, remember, and it's the concentration of ammonium and hydroxide. So if you were to determine the concentration of ammonia, you would simply say 0.4 minus 0.00268, and that would give you your concentration of ammonia. So that comes out to be 0.39732 molar, of course. Now if you had to determine the pH, that was the aim, that was the question. So you would say, well, I have the concentration of hydroxide in place, which is 2.68 times 10 to the negative 3. If you take the negative log of that, so if you try to determine the pOH, that will give you the number that you will get. You will need to subtract that from 14 to get the final value in terms of pH. So let's take a look at that. And the negative log comes out to be 2.57. And since pH plus pOH is equal to 14, pH is going to be equal to 14 minus 2.57. So that's going to be 11.43. And that will be the pH of the solution. Now, realize that sometimes Ka and Kb both are related to each other. So sometimes the value of Kb may not be given to you directly. And you can still determine the value of Kb using Ka. So what that means is that the conjugate acid with its base, or the acid with its conjugate base, those two are basically like two faces of the same coin. So let's take a look how. So if you consider maybe the ammonium-ammonia system. Hopefully you can see that ammonia is your base, and when it accepts a proton, it generates the conjugate acid. That conjugate acid has the capability to react with water and generate hydronium ion and loses that proton. So what happens is that water basically relieves the ammonium ion of the positive charge. So water would just basically pick up that proton and generates hydronium and ammonium, or ammonia. And if you were to write down the equilibrium constant, that equilibrium constant would be the acid dissociation constant for this conjugate acid. And so you would say hydronium ion times ammonia divided by ammonium gives you the Ka for ammonium ion. When you use the ammonia, the base component of this conjugate acid base pair system, you would say that ammonia will react with water, and in the process, since water is more acidic as compared to ammonia, it's going to generate hydroxide by losing a proton, and the ammonia will generate the ammonium ion. And in this process, the Kb is going to be ammonium times the hydroxide divided by ammonia. Now, if you end up adding both of these equations, you would see that the ammonium is on both sides of the equation, so that's going to cancel out. Likewise, ammonia exists on both sides of the equation, so that gets cancelled as well. What remains is 2H2O plus hydronium gives you the hydroxide. Turns out that if you add two equations, their Ka and Kb must be multiplied. And so if you look at Ka times Kb, you would be able to say hydronium times ammonia divided by NH4 times NH4 times hydroxide divided by ammonia. So ammonia and ammonia cancel, ammonium and ammonium cancel. What remains is H3O plus times the OH minus, which is nothing but Kw and has a fixed value of 1 times 10 to the power of negative 14. So Ka times Kb is equal to Kw. This holds true for conjugate acid-base pairs only. What that means is that if you have the ammonia-ammonium system and the Ka of the ammonium ion is given to you, you should be able to calculate the Kb for ammonia by using this relationship by simply dividing 1 times 10 to the negative 14 by the Ka number. You should be able to determine the Kb for ammonia. Just to kind of, just to check that, you can consider to solve an example such as the ammonia-ammonium system to kind of check, but that relationship will hold true for only conjugate acid-base pairs. All right, let's go forward. So in the previous slide, I told you that for any net reaction that is being added, the equilibrium constants are going to be multiplied. Likewise, for any reaction that will be subtracted, the equilibrium constants will be divided. So if you add two equations, then the equilibrium constant, the k's are multiplied. If you subtract, then the k values are divided. Okay, so in that sense, it's kind of similar to Hess law, that you can't just keep the equilibrium constants, independent of the reactions. You have to do something about the overall net reaction as well. And so again, Kw is equal to Ka times Kb for any conjugate acid-base pair. And so if you knew the acid dissociation constant, you will be able to come up with the base dissociation constant because Ka times Kb is equal to Kw. Again, hopefully using this relationship, you can see what I said in one of the videos in the earlier part of the chapter, that if your acid is kind of strong, if this acid ionization constant is a really large value, it's a large number, then the Kb will automatically become a small number. Because realize, if the product is going to be equal to Kw, that basically tells you that a large number on the left hand side, when it becomes a large number in the denominator on the right hand side, essentially it's going to decrease the value of Kb. So how does that culminate concept wise? That basically means that if your acid is strong acid has weak conjugate base. And so, those of you who have to take up organic, this idea is of real importance. Week 2 of class, I will be discussing this in great detail, where we would be looking at several organic acids, several organic molecules, and making predictions as to how you can say which is a better acid, which is a stronger acid as compared to another molecule. So, all right, the tail end of this chapter is about the acid-base properties of salts. Now, first off, when you think about salts and how salts are generated, what comes to mind is that an acid must neutralize a base and an ionic compound called a salt will be generated. And in that process, a molecule of water is given off as well. And we call this reaction an acid-base neutralization reaction. And the first one that comes to mind for most people is HCl reacting with base, maybe NaOH, and that gives you NaCl and water. And so HCl and NaOH are aqueous, NaCl is aqueous as well, water is liquid. So realize that these salt solutions that are generated, these can be either neutral, acidic, or basic. And ultimately, it depends on which acid is reacting with which base, and that decides the kind of solution that will get generated. But to make the long story short, a more qualitative sense, a qualitative treatment of what your overall solution is going to look like after the acid has been mixed with the base is that you basically check the strength of that acid and that base. So if both the acid and the base, if these are strong, that will lead to a neutral solution. So NaCl is going to be a neutral solution. On the other hand, if you mix, let's say, strong acid with a weak base, so you have strong acid and a weak base. Since the acid is strong, the overall solution also is going to end up being strong. A good example of this would be something like, let's say, HCl reacting with ammonia, and that gives you NH4Cl. And so the solution of NH4Cl that is mildly acidic in nature, pH usually is between 5 and 6. If you consider uh, a solution of weak acid and strong base, so something like maybe carbonic acid or maybe acetic acid, CH3COOH, and I'm going to treat that with NaOH. And again, when you do the neutralization, you end up getting CH3COONA plus water gets generated. So we are saying that the sodium acetate is going to be mildly basic in nature, and the reason for that is because you have a weak acid and a strong base system. And if you have a weak acid, a weak base system, in that case, it really depends on both the Ka and the Kb values of the acid and base. Whichever is stronger is going to control the acidity or the basicity of your overall solution. Okay, so let's consider first solutions of alkali metal cations. So that means group 1 and group 2, without keeping in mind the beryllium, for instance, which is really small. So in those cases, so a great example, sodium chloride, NaCl. So suppose you take NaCl and maybe you have like 0.01 molar sodium chloride, and you're going to add water to that. Okay. And just for a little bit, I'm going to write water as HOH and kind of see what you guys can come up with. Realize that all that water does is it basically comes in and it cleaves the bond between sodium and chloride, and you end up getting Na plus and Cl minus as dissociated forms. You don't see sodium or chloride to react with water to form the hydronium ion or the OH negative. So it's not that you would be able to have the sodium react with the OH and have the H plus react with the Cl. That is not seen. And the reason for that is probably because Cl negative is essentially a conjugate base of a strong acid, which is HCl. And so, if we just discuss this, if your reaction acid is very, very strong, then your conjugate base is going to be super duper weak. And for that matter, Cl negative would not be as powerful to be a great candidate for this reaction to take place. Now, if you compare that to HF, okay, and you treat that with sodium hydroxide. So let's write that somewhere. You have HF, so that's your acid. And that gives you NaF and water. So my salt in question is sodium fluoride. Now what would happen if you take sodium fluoride, NaF, and you put that in H2O? Turns out the fluoride behaves a little bit different than the rest of the halogen or halide ions rather. Turns out that F negative is the base of HF, so in the deprotonated form. So what that means is that it's going to be way more basic because the HF, the starting acid, is acidic. So again, I'm going to rely on the fact that Ka times Kb is equal to Kw. So what we are saying is that if this is low, then automatically Kb will be a higher value, and that gives you some information about fluoride. And so one can safely say that if F negative reacts with water to give you HF plus OH minus. And so the factor that basically favors this reaction is the formation of the HF bonds. Realize that this will require breaking up of the OH bonds, and turns out that the HF bonds are stronger as compared to the OH bonds. On the other hand, when you compare the HX, that means the HCl, the HBr, the HI bonds, with water, you would see that water is stronger. And so that explains that other halide ions do not react with water. On the other hand, solution of sodium fluoride are weakly basic in nature. Now, if the salts contain a conjugate. Okay, let's talk about salts that yield acidic solutions. So, like we discussed, a situation with, let's say, ammonium chloride, and so ammonium chloride is a weakly acidic solution. So again, considering NH4Cl, that must be obtained from NH3 plus HCl. And so one can say that essentially we have conjugate acids of weak bases, and hence it is going to be acidic solution overall. So one can say that while chloride ions typically will have negligible strength as Bronsted-Lowry bases, the ammonium ion, so chloride is not going to go through the Cl part. That's not going to go through a reaction with water. But ammonium ions are conjugate acids of a weak base ammonia. And so these are weakly acidic and they will produce some hydronium ion. What that means is that you have your NH4 plus that's going to react with H2O to give you ammonia and water. And so, just like we were talking about earlier, flow with the case of HF, the fluoride, the F negative, was going through a hydrolysis process, and it's the differences in the bond energies which ultimately, drive a reaction such as this. And so here you can say that the OH bond in the hydronium is going to be stronger than the NH bond in ammonium, and hence it must be broken. And that is the reason why NH4Cl is going to be weakly acidic. So again, if you have to summarize, if you have to classify, or if you have to pick which particular salt is acidic, basic, or neutral, you will say that it depends on whether they include cations that are conjugate acids of weak bases, or anions that are conjugate acids of weak acids, or both. So if you have, let's do a little bit of practice so we know what we are talking about. So in general, what the slide tells you is their ability to remain hydrated is going to be more as the metal ion size decreases. So in that sense, one can say aluminum is going to probably show you maximum hydrolysis power, and so would the transition metal cations. They have a high charge, so they will go through a hydration as well. In this case, recall this concept from chapter 11 as well. Now, if you consider something like sodium acetate, that would generate a basic solution because the cation part is neither acid nor base. So consider sodium acetate. What we are saying is this Na plus doesn't care, it doesn't interact with water. But for acetate, you can write down for sure that with water it will give you acetic acid and OH negative. So one can say that water has acted as an acid, and acetate has acted as the base, or in other words, it has undergone hydrolysis to generate acetic acid and the hydroxide. And so again, it will be the ability of the acetate unit to go through this reaction of hydration and generate the hydroxide. And since it is generating some hydroxide, you would say that this is going to be a weakly basic solution. So again, the cation is not going to decide acid or base here. What will decide whether it's acidic or basic is the weaker component. So whatever is weak will have a tendency to go through hydrolysis, and that's what dictates how your overall pH of the solution is going to look like. So let's maybe I'll give you a couple choices, and then we can discuss how that. So if you consider, let's say, NaClO, NaClO, and your aim is that you're supposed to label that as an acidic, basic, or neutral compound. So realize that when you're thinking of how the salt would have gotten generated, essentially when this dissolves, it gives you Na plus and ClO negative. So now if we think about what undergoes hydrolysis or not, sodium is not going to undergo hydrolysis, so we don't have to worry about that. However, ClO negative is the conjugate base of the hypochlorous acid, and that is a weak acid. So you can safely say that ClO negative plus water gives you HClO plus hydroxide. And so, because of this hydrolysis of a weak um, uh, conjugate base of a weak acid, essentially, one can say that these salts, these are going to be weakly basic as well. So again, depending on how you got that salt. So another way to look at that in a qualitative sense is if you look at NaClO, that must have been obtained from NaOH and HClO. NaOH is a strong base, HClO is a weak acid, so overall whatever is strong is the one that wins, and so the pH is going to be more alkaline in this case. Okay, let's take a look. The question says, if you have acidic cations and basic anions, so salts that contain acidic cations or basic anions. So these are like um, solutions. Looking at the Ka Kb values, you can determine the pH. So if the value of Ka is much higher than the value of Kb, you say that an acidic pH is going on. If the value of Ka is less than Kb, that means a basic pH. And if the two are equal, then you say that the pH is going to be 7 and is going to be a neutral case in that particular scenario. If you have like a weak acid, weak base type of a system, in that event, you're going to say that it's going to be exactly equal or neutral if the Ka-Kb values are equal, and then you use the same rules as previously. So it really depends very directly on the values of Ka and Kb in this particular case. Let's try to solve another question on the basis of this. So suppose I have like 0.1 molar sodium carbonate. Okay, and so it's a sodium carbonate salt, and that's present, in the ecosystem, and our aim is to basically determine the pH values of solutions. In this case, it's a solution which is for a weak acid, weak base, and it's coming from sodium carbonate. So if you think about, well, what kind of species would be available, realize that sodium carbonate is CO3 2 negative, and its conjugate acid is, you add a proton for that and you will end up getting HCO3 negative. So there is this equilibrium that is set up here, where the carbonate and the bicarbonate values are basically linked to each other, because there is a ionization that can be written for carbonic acid, which is a two-step ionization. So realize that the conjugate acid HCO3 will react with water and give you carbonate and hydronium ion. And the Ka2 is 4.7 times 10 to the negative 11. And the reason why I say it's Ka2 is because, of course, if you just would have taken H2CO3 and added water to that, that would have taken one away. So this would have been your Ka1. So you realize what we have here is Ka2 number, and you should also realize that when you're looking at sodium carbonate, the sodium component is not going to go through hydrolysis, however, carbonate would. So what would the reaction be if you take carbonate and you put water into it? Turns out it's going to give you the HCO3 with a negative charge, and it's going to generate OH negative from that reaction. Okay, so two reactions. One is the reaction of bicarbonate with water, which is giving you carbonate and hydronium ion, and the other is the reaction of the hydrolysis of carbonate with water, which is going to generate bicarbonate and hydroxide. Now, for this particular step, you can write down the Kb1 as HCO3 times hydroxide divided by carbonate. That's one step. Now, we called it Kb1 because it describes the first of the two possible um, um, reactions that produce the hydroxide ion. And of course, the second reaction would basically go through another bicarbonate with water, yielding carbonic acid and another hydroxide ion. So that would be Kb2. So what I just said is if you take HCO3 negative, which just got formed, and you put another molecule of water, that's going to give you H2CO3 plus OH negative, and that equilibrium constant will be Kb2 because it's the second ionization uh, in this case. Um, Likewise, if you had to calculate, if you had to write down the Ka2 value for the carbonate, that comes out to be CO3 to negative times hydronium, and you're going to divide that by the bicarbonate. Turns out that this literature value is 4.7 times 10 to the negative 11. Now, if you wanted to compare and contrast the Kb1 value for the carbonate, which is going to basically help us understand and figure out the numbers for this particular question. If you want to compare that, so this equation in blue, and you compare that to the equation in red, you would see that both of those feature carbonate and bicarbonate. And in one case you have the hydroxide, and in the other case you have the hydronium ion. And you also know that the hydronium ion, H3O plus, and the hydroxide are linked with each other using basically Kw, right? You know that the hydronium times the hydroxide is equal to the Kw. And so at any given point of time, hydronium could be written as Kw divided by the hydroxide ion. So if we can say that hydronium is going to be equal to Kw divided by the hydroxide, and we kind of plug that number into the Ka2 because looks like only that is the literature value that is known to us. We could say that Ka2 is going to be equal to carbonate CO3 to negative times the Kw divided by hydroxide and HCO3. And for I want you to compare essentially the Kb1 value that was given, that had bicarbonate times hydroxide in the numerator, carbonate in the denominator. And now I have written that carbonate as the numerator and hydroxide and bicarbonate in the denominator. So can I say that essentially this part, that entire part, is nothing but 1 over Kb1, or that Ka2 is going to be equal to Kw divided by Kb1. And if that is true, then I could just simply say that Kb1 can be determined as Kw divided by Ka2. And since Kw is just 1 times 10 to the negative 14, if I divide that number by the given number, 4.7 times 10 to the negative 11, I should have my value of Kb1, which comes out to be 2.1 times 10 to the fourth. So realize you can determine the values of KBs and KW and KAs, provided the other number is given to you. Now, once you have this number, you can use that to set up the ice just as we have done previously. So I leave that up to you. But I wanted to take the time to kind of go over how you can change, how you can use the acid dissociation constant of one of the species, provided the other is given to you. And so you can use that to your benefit to get the Kb value from the species. Okay. Now, let's take a look at the final aspect of this chapter, looking at the factors that basically determine the acid strength as to which is a more strong or stronger acid. Basically, it mainly is determined by the strength and the polarity of the HA bond. I mean, there are other factors as well, especially in case of organic acids, and we are going to take the time to go over that in good detail. There's a chapter based on that in organic one, but there are some other things that are kept in mind from the perspective of a Gen Chem 2 aspect. So that's what I'm going to focus on in the next couple of slides. Really, the strength of the HA bond, where A is your conjugate base, that essentially decides in the acidity. If this bond is weak, one can say that that particular compound is going to be more acidic. So one could also say that the polarity of the bond kind of dictates um, how how strong that bond is going to be. So going back to what we discussed early on, HF, if you compare that to H2O, HF is going to be more acidic, but that has got to do with the electronegativity of F. But now if you compare HF to, let's say, HCl, HCl is a stronger acid than HF because the HF bond is stronger as compared to the HCl bond. Both hydrogen and fluorine, they happen to have, or the valence electron in case of hydrogen, that's the 1s1. The valence electron is residing in the 2p5 in case of fluorine. Those are closer in energy as compared to the 1s in hydrogen and the 3p in case of Cl. So hopefully based on this argument, you can say that HBr is going to be stronger than HCl and HI is going to be the strongest acid. So two things again. Greater polarity means better acid, which was the reason why HF was a better acid than water. And the other reason that I just talked about was the size, or the fact that down the group, the size increases for I minus, so that bond is going to weaken. All right. And that's what I say here. So HF, notice, has a bond energy of negative 567 kilojoules per mole. HI is negative 299. And so one can say, since HI is a much weaker bond, essentially that's going to cleave much easily. And for that reason, that's going to be most acidic. So acidity is in this direction. And that's what we say here. HF is a weak acid. HI is a strong acid. Within a period, it depends on the electronegativity, and hence one can safely say that HF is going to be the strongest acid. So if you compare CH4, ammonia, water, and HF, that bond is going to be most polar. Methane is going to be most nonpolar or covalent. So that's going to be the weakest acid, because carbon is not going to be to give you some polar bonds, and so one can say that HF is going to be the most polar and also most acidic. Most acidic. Another factor that one can use is basically the stability of the conjugate base. The acid strength basically increases if your conjugate base is going to be more stable. And one can talk about the stability based on where that negative charge is present. So if that is present in, let's say, an sp hybridized orbital, or if it is resonance stabilized, those are situations where you would say that you have a very stable conjugate base. So that particular acid would rather spend majority of its time as that conjugate base. In other words, it would have given up that proton very, very quickly. So what we are saying is something like, let's say, acetic acid with water, that gives you CH3COO negative plus H3O plus. Turns out that when you draw the Lewis structure, the Lewis diagram of the acetate, this is the acetate unit, so this is a Gen Chem 1 concept. These negative charge comes over here, the pi system moves, and there is resonance in the molecule. And if there is resonance in the molecule, that means this is going to be very stable. So if acetate is stable, don't you think that acetic acid would rather donate that proton and achieve that stability, because what you've gotten is essentially something that contains resonance. So that's how you would be able to predict the acidity of a given acid. If your conjugate base is very stable and the negative charge is at its proper place, then you would consider that that more stable. Okay, so the question here is, let's look at HClO4, HClO3, HClO2, and HOCl. You have to draw the Lewis dot structures for the acid and the conjugate base, and then list them in the increasing order of acidic strength. So I'm just going to do this for you. That's the structure of the perchloric acid. That's the structure of the chloric acid. This is the structure of your chlorous acid. And that's hypochlorous acid. Notice that you can draw resonance in these molecules when the proton is lost and you have a negative charge. That negative charge can be given, the electrons move. Likewise, in case of this proton, once gone, that negative charge can be donated, these electrons will move. And the same story goes on in the third case as well. Notice there is no resonance in case of the last case. So there is no real need for the HOCl to kind of give up that proton, because the conjugate base is not going to be very stable for it. Turns out greater is the number of resonance structures that you can draw, higher is the amount of resonance. And since each of these oxygen atoms are essentially equivalent, one can say that you would be able to draw 3 to 4 resonance structures, 3 resonance structures in case of the first conjugate ion of perchloric acid. You would be able to do only 2, and that is excluding the one that we already have. And in case of the first one, you would be able to draw only 1. Greater is the number of resonance structures, higher is the stability, and so that makes the ClO4 negative, so the perchlorate, that is most stable, and ClO with the negative charge is least stable. So hopefully you can see the acidity is going to be in that order as well. So stability of the conjugate base is going to stabilize or provide a greater acidity for the corresponding acid. All right, let's talk about Lewis acids and bases. So far, all of this has basically involved Bronsted-Lowry bases, according to which proton acceptor was a Bronsted-Lowry base and a proton donor was a Bronsted-Lowry acid. So Lewis, he proposed that a Bronsted-Lowry base, such as ammonia, is able to accept a proton because it has the ability to donate its lone pair of electrons. So what he suggested was actually the fact that you can consider a Lewis base, such as ammonia, which is also a Bronsted-Lowry base. And so a Bronsted-Lowry base is basically also, in this case, also a Lewis base. So Lewis is a more wider definition. And what he suggested Lewis acid as was just the opposite. And he considered that a Lewis, while a Lewis base is going to be an electron pair donor, Lewis acid is going to be an electron pair acceptor, and it's going to accept electrons. So hopefully you can see that if a Lewis base is donating electrons, that means it should be rich in electrons, should have a negative charge or lone pair of electrons. Lewis acid, on the other hand, should be positively charged or should be deficient in electrons if it wants to accept electrons as a Lewis acid. So over here, I'm showing you how a Lewis base ammonia is giving its electrons to a Lewis acid, which is a neutral molecule, and it ends up giving you an acid base dot. Recall that boron does not form electron, like a complete octet for itself. It doesn't form that because boron is group 3, and so it has 3 electrons of its own, and fluorine is going to give you 1 electron. Rest everything else for fluorine is complete, and so at any given point of time there are only 6 electrons around boron, and since it inherently lacks these electrons, the lone pair of electrons that are present on nitrogen can serve as a great source of electrons for boron, and hence this adduct is allowed. Let's take a look at the final slide. The question is, for each of the following reactions, identify the Lewis acid and the Lewis base. So again, the electron donor is Lewis base, electron acceptor. So these usually will contain metal ions. That will be the Lewis acid. So negative charge, that must be Lewis base. Metal, that must be your Lewis acid. Ag, that's the positive charge. Lewis acid will accept electrons. Ammonia with its lone pair of electrons must be Lewis base. Hydroxide with a negative charge, Lewis base. SO2 is going to be the Lewis acid. Likewise, Cr3 plus is going to be your Lewis acid. Water with a lone pair of electrons is going to be your Lewis base. And that is it.